Okay, guys, question I think was CF3 here. Carbon with 3 fluorines, right? Which carbocation is more stable? One on the right.
And because the negative's moving that way?
Because these fluorines pull. I mean, you don't want to have a carbocation which is already poor, and you got fluorines just pulling more. You'd rather have donation towards a cation. You don't want to form a cation where you're going to have a lot of pulling away. That's just going to make it worse. It's going to make it less likely to form. The one on the right is more likely to form and more stable. Okay.
Bless you.
Let's finish up this here at the bottom. Okay, looking at deprotonating terminal alkynes. Yes, you can do this. Strong base. You cannot do this with hydroxide. Actually, the reverse reaction is favored. An acetylide anion will take a proton from water and go this way. Okay? That's the basis of this carbide lantern. Handheld lantern, or you can even have it on your helmet and have a little flame up there. What is calcium carbide? CaC2. You got a Lewis structure for C2? How about something like this? C2. What's the charge of C2? 2 minus, because calcium is 2 plus, correct? There's C2, 2 minus. And then the calcium sits with this to be the counter ion. 2 plus charge, 2 minus charge. Calcium carbide can be made. It's been made for a long, long time. Okay? What happens if you put, this is like a double acetylide anion. What happens when you put this in water? Same thing here. Anion reacts with water, right? This is going to take an H from water. You can do your acid-base mechanism. What do we get when each carbon takes an H? That, right? It's the reverse reaction. We're doing it with carbide. This is acetylene. You would also make calcium hydroxide. Acetylene, that's a gas. Okay? And this will burn. And if you do it, I sent a video about that. You put one in the chamber, you put water, and it's combined. And when it's combined, it generates acetylene, and out through the tube, you can light it. Look at the video. So that's the reverse reaction. These acetylide anions reacting with water, going back and putting the H on. They've been doing that for 200 years. Imagine that chemistry on your little helmet there and your flame. Yeah. You got to get the flow just right, or it might explode. I don't know. Okay. We will generate acetylide anions and use them as nucleophiles later in the course. I'll say, do you remember how to generate them? And you guys will go, don't do that. Right here, this is how you generate them. That is the end of the material. End of the material with test 2. Right there. We covered alkyne chemistry. Question?
So, when this, you got this in the supplement class, so would this one be the same as the one we just went over? It said, oxygen compound B compared to amino acid that would be how you do the last one?
No, we're removing H's on the last one. What type of compound you're looking to make? What type of compound you're looking to make? No. What type of compound are you looking to make, prepare, synthesize? No.
Or this one?
Is that what you're looking to make? Yes.
Yeah.
Yes.
So,
Yes. It's a transalkene. Okay. How do you make transalkenes? What reaction have you seen to make transalkenes?
Production.
What reaction have we seen make transalkenes? And I'll give you a hint. We did it on Wednesday.
Dissolving metal reaction.
Do what? It involves what?
Production.
Reaction of an alkyne. Alkyne was the starting material with what reagents? Yes. Did we say that that was a way to make transalkenes? Transalkenes. Did everybody read this multiple times until you understood what was going to happen below? For example, do you know it's a partial reduction? Because I think that's hugely important. That's why I listed this stuff in bold. Transalkenes. You got to know what we're making. You want to remember it, and when somebody ever talks about, oh, let's see, that's a note card. What reagent do you use for this? And then it's a radical mechanism. You've got to categorize your thinking and keep it from just being this. For example, what did we do on Monday? You should be able to give about 4 or 5 sentences of what we did. So I would recommend, if you want, do whatever you like to do well, but I'm recommending this to do well. You've got to know what you did in class, because if you don't even know what you did in class, how are you going to go from there? Right? Then this is below. So it's got to be very systematic and recognize what we are doing, because it's a lot of information, so you got to organize your information. Then when you hear a new topic, you're like, okay, what's this new topic about? Okay, this. Then you're ready to go and link what you know to that, because you hear these. Okay. Okay. That's the material. A couple of you have asked about moving the test from Monday because of pre-registration. We'll do that. Test will be on Wednesday. Okay? Monday we'll begin new material. New material we begin with resonance. This is a resonance handout. On Monday, we'll see what type of questions you have that come up after studying over the weekend. Let's look back at some things. Questions? Anything about thermodynamics, kinetics? Reaction coordinate diagrams? Any questions there? Good to go on all that? Any questions there? Okay, let's look at intro to alkenes, including nomenclature. Any questions there?
Dr. Stevens,
Yes.
can we take a look at one of the multiple choice questions for exam 2?
What page?
It's on page 50, number 16.
50?
Yes.
number what?
16.
16, 1-6?
Yes.
Okay. Let's look at it. That's alkene chemistry. Let's when we get to alkenes a little bit. First, anything about the nomenclature or the handout on Intro to Alkenes?
Did you have an alkene on both ends? So just say you had
Stereochemistry handout. Purple one. Purple one. Go ahead. Sorry.
that's all right. I just don't, if you have two alkenes in the same chain and they're at the end, so neither one has priority, how do you name that?
You mean something like this?
Yeah. Oh no, it would be on the end on both ends.
Well, you mean this?
Yeah.
This is a diene. We haven't covered
Oh, okay.
nomenclature of dienes.
Okay.
That will actually be in test 3.
Okay. I've seen
Okay.
that in the book. But,
So diene, tetraene, we're only doing one ene right now.
okay, perfect.
This question here included some alkenes. I don't think we did this in class. How many chirocarbons did this molecule have? That was like an OH or something. Chirocarbons. How many did you get?
6.
5?
4.
Let's see. 1, 2, 3, 4, 5. Are those all chiral? Any others? That's not chiral there. 5? Someone say 6? We missed one?
What about that?
Might see another chirocarbon. Okay, how many other stereogenic sites? 2. Each alkene is stereogenic there. How about these alkenes? First of all, you would never call these alkenes. That's a benzene ring. They're not alkenes. They don't react like alkenes. And also, those pi bonds are not stereogenic. In the 6-membered ring, the double bond cannot be stereogenic because it has to be basically cis. If this bond here came this way, you ain't going to make a ring. So I see 7 stereogenic sites. 2 to the 7 is what?
A lot. 128?
128? Is that right? It's 2 to the 7. Sounds like 128. Could you draw all 128?
Not on the test.
You could have all these chirocarbons being R and both double bonds being trans. That would be 1. You could have them all R, 1 double bond trans, 1 double bond cis. That'd be just all the variations. Okay. Other questions about alkene nomenclature? EZ, stereogenic sites. Any questions there?
Do you have the handout that you went through in the video?
Yes.
The last structure, can you go over the name for that? That one? Yeah.
Very bottom,
Yes.
you want a name?
Mhm.
Did it ask for a name? What did it ask for? What are we doing with this structure? Just E or Z?
Yes. But what if we name it?
We can name it, but was there anything else that was asked you to do here that I did not answer? For example, is this E or Z? It's Z, isn't it? This one is Z? Did I do it in the video?
Yeah.
Okay. You want to name this stuff?
Yeah.
Okay. La. Alkene has to be in the longest continuous chain, so might as well start right here with 1. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That is a 1 pentene. Yeah? What's on the 1-pentene? I got a fluorine, a bromine, and it looks like a complex sub. Alphabetical order, that's going to be chloro, bromo. Bromo is probably going to come first. 5-bromo. Probably then next, this is the 2 position. What's at the 2? Ethyl with a chlorine. Coming off, that's going to be 1,2. 2-chloroethyl. At the 2 position, we have a 2-chloroethyl. And then at the 1 position, we have a fluoro. Fluoro is spelled fluoro. 1-fluoro, 1-pentene. This one indicating where the double bond is at the 1-2 position. 1. How's that name look? Is that what you got?
Yeah, but I was confused with the two fluoroethyl part.
That's a complex sub, just like
Yeah.
you would have named a complex sub on alkanes or anything. The first carbon coming off your main chain is the 1 of that sub. So the chlorine is on the 2 of that. Does it make sense? Just like what we have done before. That's a 2-chloroethyl. 1-fluoro, 1-pentene. Good. Other questions about that handout? Easy nomenclature? Alkene chemistry. Questions there? THC, yeah. How about here? Did we do these? Did we do this one with the ICL?
Would I or CL make the 3-membered ring?
Well, what's the reactivity here? Is it schizophrenic or is it truly some polarity? Right? Chlorine's electronegative, partial plus, partial minus. These electrons are going to attack which one?
The I.
The iodine attacks H plus. This is nuclear. This is electrons. It attacks electrophiles, which are electron poor. This attacks here. Did we do this one in class?
No.
Where are we going to make cation? Top or bottom? Bottom. Attacks iodine. Cation, tertiary cation. We kick this off, yeah. Chlorine. What's going to happen here? Anything? Is this really formed? A back bond. So I don't think this is really formed. It's going to happen at the same time. And we get the iodonium ion. We can draw it like that. Right here, what type of stereochemistry do you have right here? Carbocation is trigonoplanar. There is no stereochemistry. It's planar. Right here, that's tetrahedral because there is an H. This iodine is either forward or back. I mean, I can draw it forward or back. Since I drew it forward there, it needs to be forward here. It's forward. It just comes and attacks the cation, and so the other bond has to be forward. But this could also be reversed. This could be plus enantiomer. Okay, Cl minus comes in. Which carbon is it going to attack, top or bottom? Bottom. It's the same place as the cation would be. Electrons come in here, kick off the iodine. What are we going to get? Iodine just gets kicked off. The new bond to the chlorine is going to be what projection? It's going to be back. Because the thing is kicking off is forward. Comes in backside, or opposite side. This actually pushes the ethyl group forward. Now I should have drawn that maybe a little bit up to leave room for that, but that works too. There's your product. Plus what? Plus an enantiomer, because this is chiral. The enantiomer would come where we just reversed everything along the way, because here, this is flat. I'm assuming that this reagent comes in from the front, and that's why the bond to the iodine was front. But we could have also made that bond back. If we made that back, then both of these would be back, that would be forward. And so if this was back, the chlorine would have to come in front. And so everything would be reversed if you just did it the other way. And that leads to the enantiomer. While we have this up here, let's address something that we did not do in the stereochemistry. I believe it's in the purple. Yes, on the back side. F. Regioselective, stereoselective. We've done a little bit of this, but we need to do a little bit more. Reaction on the board that we just did. Does that reaction, is it regioselective? Does it exhibit regioselectivity
Yes.
that we just did? Why does it exhibit that?
More stable.
What about this reaction indicates regioselectivity?
Difference in substitution.
Do what?
The difference in substitution.
What do you mean?
One carbon is more substituted, therefore it's more stable. Lies with the carbocation.
I'm still not.
Iodine's always going to be in the top.
Yes, iodine's going to be here, not here. Did we draw the product? Because whenever you add things across double bonds, I mean, we ultimately added an iodine and a Cl across the double bond. Used to be a double bond, now there's an I and a Cl. Was it random? Did we have I here or I there? Or was I only in one place? Only in one place. It's only in one region. This reaction is regioselective. We did not get the iodine here and the chlorine there. What if we were doing bromination, Br2, and you put a Br there and a Br there? Would that have exhibited regioselectivity?
No.
No, it's like there's no possibility, because if you switched them, it'd be the same thing. But this reaction does exhibit this. Regioselective. Now, some questions may say regiospecific. There is a slight difference for us. Consider them the same. You see regiospecific. All right? I don't want to get into the slight differences. This reaction is regioselective. Some reactions we've done are not. That is, you'd end up with sort of both. And if you did get both, you would say it's not regioselective. This one is. Is this reaction stereoselective? Did we get one type of stereochemistry over another? What did we get?
Enantiomers.
Well, what does that mean? So you're saying it is stereoselective or not?
Yeah.
But it has to be trans.
How is it selective if we got
Yeah, it's not because you can get either one.
Oh, yeah.
You don't get just one.
do we only get one?
No, we got it.
Okay. But we have to be careful when we say stereoselective, because there's two types of stereo. There's an antioselective. There's also diastereoselective. But first, let's do an antioselective. Is it an antioselective? Did we get one enantiomer over another? No, we got both. That's That's what this means. We got that plus the other. No. All right? All right? What about the diastereo selective? That's a mouthful. What does that mean? One diastereomer over another. Now, it's easier when we do erythro-3O because we haven't really this. Now, what if I showed you this product? What if I showed the iodine here and the chlorine here, thus the same regiochemistry? But what if I drew the chlorine like this and the ethyl like that? Did we get that product?
No.
Plus it's an enantiomer. Did we get this? No. So we got that, not that. What's the relation between this and this?
Diastereomers.
These are diastereomers. So, did we get one diastereomer and not the other?
Yes.
Yes. It is diastereoselective, but it's not an antioselective. The diastereoselectivity comes from the mechanism because it's a backside. When you did bromination a week and a half ago in lab, or last week in lab, was that reaction diastereoselective? Yes, you only got meso. The DL would be the diastereomer. Now meso was not chiral, so the asking if it's an antioselective doesn't really apply because there's no enantiomers possible for the meso form. By the way, last week in lab, did that reaction form any DL? Or did it form only meso?
Meso.
Gotta be careful. You isolated meso. How do you know it didn't form some DL and you just didn't isolate it? So you gotta be careful when you say, did it form it or did I isolate it? I think all of you proved that you isolated meso, but that doesn't mean some DL wasn't formed and maybe it was removed during the recrystallization. So you gotta be careful about that. Minor point. Okay, so that's the idea of these things here. But guess what? I told you several times early on, none of the reactions we're doing right now will ever be enantioselective. We're never going to get one enantiomer over another right now. Remember who said that? So you knew the answer was that. It was already no. Now, next test, we'll get some enantiomers. But that's only going to be because we'll start with an enantiomer. Did we do the bottom one here? DCl. What type of product did you get there? This here? Is that right? What is the double bond attack? The D. Just like here attacks the I. Now this you can actually, if you want to, you can show it ionic if you want. Don't show that ionic. Just attack where you gonna make cation. Bottom, right? So the D, and then here. Chlorine attacks here, right? Is that how we get it here? What's going to be the stereochemistry of the chlorine compared to the D? Is this a real cation? Yes. I mean, D does not have a lone pair. It's like on the backbone. Is this a true cation? How does the chlorine attack?
Would be the same direction.
How does the chlorine attack the carbocation?
Yeah.
Both sides, right?
Both sides.
Okay. Right? By the way, in the first handout, Where was it at with the nomenclature, not nomenclature, but the alkene? Must be alkene warm-up. I don't have that. Is there another white page, colored page? Yellow, thank you. Right? It's all here, right? How's the nucleophile type cation?
Either way.
Both right? I gave you that very early on. It's the basis of all our mechanistic stuff. So hopefully you spent a lot of time on that because it was going to help us all the way through.
And that's because it's planar, right?
It's planar. Yeah. We drew a cation on a piece of paper, yeah?
Right.
And how are you going to attack it? What if it's here? You guys attack it that side, you guys attack it that side. And when you're dealing with 1 billion molecules, it's just going to be 50-50. It was all there. So what type of outcome is here? Is this reaction regioselective? Yes, the deuterium's going to be here, not there. Is it enantioselective, diastereoselective? What type of stereochemistry selectivity do we have here? Answer is absolutely none. You're going to get all possible stereoisomers. Because this can be dashed or bold when it adds. For example, if it can be bolded, but that is tetrahedral. If it's bolded, how is this one going to be when it comes in?
Either way.
Either way, it doesn't matter what that is. So you're going to get bold dash, you're also going to get bold bold. But this can also be dashed. And if that was dashed, how would this end up? Either way. So you get dash dashed or dash bold. You're going to get all four. Because, why do I mean all four? How many stereoisomers possible for this compound?
4.
I got 2 chiral carbons, how many possible?
4.
4. Guess what? You're going to get all 4 from this reaction. There's no stereochemistry, no stereoselectivity at all. It's neither diastereoselective nor enantioselective. All 4 form. Does it make sense that all 4 would be formed there? I think I'm going to skip some of these because the better place to work them is on the stereochemistry page. Is there anything in this, the big alkene handout you want to look at in particular? Alkene reactions. Let's work one here. Stereochemistry. At the bottom here, we work the first one. Before we do that though, let's do one up here real quick, because I don't think we did these 3 in class. You have an answer for this guy here. Chiral, achiral, or meso?
Chiral.
Here?
Chiral.
Chiral? We got some people saying meso. Let's look at it. I prefer to draw it in a fissure. I mean, there's a couple of tricks, but I recommend fissure. Let's do that in a fissure. Okay, I got chlorines in the plane here. How about if we draw this here? How about if I stand here, look through there? If I'm looking through there, chlorine's going away. With chlorine going away, what side is this methyl on? It's going behind the board, so that would be the right. So with chlorine going away, methyl is on the right. That means the bolded H would be here. Okay? With this chlorine going away, I want to keep my feet on the ground. The ground is there. Chlorine going away, methyl is on the right. It's coming towards you guys. Chlorine going away, methyl's on the right. The end-drawn H is here. I found Waldo real easily. Since it's got a plane of symmetry, what's the answer? It's either meso or achiral. It's not chiral. Why would we call this meso?
Because it's plain.
It does have 2 chiral carbons. And a compound that has chiral carbons, yet as a whole is not chiral, is called meso. So it looks like that one's meso. How about this? And I want to show you a little something that is important that we haven't done yet. Anybody get an answer to this one? Meso. That was also meso? Let's do it. Let's do here. With methyl going away, chlorine is on my left. Undrawn H is here. With chlorine going away, I'll look right down there. Chlorine's going away, methyl's on my left. Chlorine going away, methyl's on the left. Undrawn H on the right. There it is on the board. Okay, this is what I want to show you, very important. Is this a plane of symmetry?
No.
No, chlorine not mirroring chlorine. But hold on, this thing has free rotation. We want to put the chlorine on the side and see if it's actually there.
No, because then
These 3, or those 3, can just rotate. And we can just rotate this like this. These 3, or those 3. And if I rotate it, I end up with methyl at the top. Oh, hold on. Actually, I want to rotate it the other way because let's make methyls at top and bottom. I kind of already see the answer now, but I'm going to rotate the other way. That way, the methyl can be down here, and that makes the chlorine go here, and the H come over here, and that's that. And you see, the methyls are now where they are if it was a plane of symmetry, but the chlorines are not mirroring. Now you can rotate the chlorine over there. You know, if I put the chlorine here, where would the methyl have been? Methyl would have been here, and that wouldn't be no good. You're never going to get a plane of symmetry here. But you can rotate those bottoms. Okay? Here's the vertical backbone. I'll make all 3 colored. Okay, that's with the methyl back, chlorine's over there. Okay? To get over here, I'm moving the chlorine back. If I move the chlorine back, well, okay. Well, there it is. Now the chlorine's back. That way, going from here to there, I move the methyl back.
H is going to be there.
No. I need to look at the methyl here. Methyl black. Let's make the methyl black. Chlorine's back. I'm getting a little confused here, so let's do it step at a time, yeah? Chlorine back, chlorine green usually for me, methyl black, okay? If I want to make the methyl back, see these 3 can just rotate, all right? But if we want to make the methyl back, which that means methyl's back over there, right? Where's the chlorine now? On the right. With the methyl back, chlorine's on the right. But you see, these can just turn. I'm doing it like this on the board, but in real life, it's spinning like this. So, you have to keep this one fixed, though. You can't be turning. Some turns are bad here. If you do some turns, you're going to go to the enantiomer. But you can turn 3 of them like this, and these 3. For example, if I put the H at the top, where would the chlorine be? Up here.
Oh.
H here, methyl here, chlorine over there. You can just turn it either way you want. Okay? That's important because sometimes you may be asked to draw it with methyl at top and bottom. This would be what you get first from your view. Then you can just turn it however you're supposed to according to directions. Either one. So I didn't find Waldo, so I'm thinking this is Carbo. How about the last one? I'm going to do a little trick here. That is, I see there's potential for that to be a mirror image because you've got 2 carbons. Each carbon has a chlorine and a methyl. Potential to be a mirror plane. If it's a mirror plane, though, it better be R and S. Because if one side's mirroring the other, it's got to be R and S. Well, let's see what it is. Chlorine's 1, carbon with chlorine is 2, methyl's 3. H is forward, clockwise, but since H is forward, this is S. Chlorine's 1, carbon with chlorine's 2, methyl's 3. H is forward, so this is clockwise, but H is forward, also S. Well, since it's SS, that cannot be a mirror plane there, because the mirror of S is not S. So that's a tricky way to do it. There's no mirror plane. Since that's not a mirror plane, that's a chiral compound. It's got 2 chiral carbons, and there's no central mirror plane. And again, there's not going to be any other mirror plane. The mirror plane is always going to be right through. Because there's no mirror plane here, because this plane goes right through the chiral carbons. And chiral carbons are asymmetric. So there would, by definition, not be a mirror plane through the chiral carbons. Anything else above here before we do one below? Any particular one you like to do? Next 3.
I want to do 4.
4. Hydroboration, oxidation here. Okay, I recommend turning these guys, which are stereogenic, before you do anything. Let's turn this and have phenyl 2, phenyl 1. Those are trans, so I'm going to turn it. They're still trans. And then we got a methyl like this. All right, I'm going to put an Ne on the end. There's the starting material. We already have projections and we haven't done any chemistry. Now, I'm not going to go through mechanistic everything because I also know some things. When we do hydroboration, we're going to put a BH2 on one carbon and H on another carbon. Which carbon is going to get the boron?
Right. The least substitute.
Correct, because we make cation here. So you know your mechanism, you envision it, okay, you can work it out. Cation here. What does the boron throw at the cation? An H. So the H actually is going to end up here, where the cation would be. Now, what's the relationship between the BH2 and the H? Are they syn or anti?
They're syn.
Syn, because the H comes from the boron. So we can say, hey, BH2, and the new things I recommend putting in the plane. Syn would be drawing it like this. Anti would be drawing the H up. But we know it's syn. There's the hydroboration outcome. This carbon, nothing changes. Everything's set. This carbon's going to have a phenyl, 2. This carbon's going to have a bolded methyl and a dashed phenyl, phenyl 1. Now this sort of moves up a little bit as it becomes tetrahedral to make room for the new thing. But there's your product. Okay? Why does the stereochemistry not change? Because the 2 steps that we showed on the board are actually concerted. Here I am, and my groups are trans. Let's do the reaction. That's it. There's no intermediate. Because the thing we do on the board is not actually formed. Since there's no intermediate, nothing has a chance to change. Your projections are still the same. There's your product. Guess what? Plus an enantiomer. Because if we had drawn these 2 straight up, let's do that. We could have also drawn those straight up, but still keep the phenyl bolded. I'm going to draw it a little bit this way, but it's still bolded. And the methyl and the, hold on, the methyl is bolded. And the phenyl 1 is like that. That's the other possibility from the top phase. Well, guess what? This is the enantiomer.
What about the oxidation?
Okay, well, what does the magic step do? And we have no change in stereochemistry, remember that? Remember that? We made a point of that? There's your products right there. All right, but draw this in a Fisher projection. Draw this in a Fisher. With what? Phenyl 1 at top and bottom? All right. Other than that, it doesn't matter. How about if this is the ground? Let's finish this up. Now looking through here. What's going away directly? With H going away, what side's the methyl on?
Right.
With H going away, and that's the ground, right? I don't want to look like this. My feet are in the air. The ground. With H going away, methyl's on the left. And phenyl 1 is on the right. Okay? With OH going away, phenyl 2 is on the
Left.
With OH going away, phenyl 2 is on the left. Undrawn H is on the right. We're supposed to put phenols at top and bottom. Well, we can just rotate this up and rotate this down. That's going to give phenyl 1 at top. What's on the left? H, and methyl swings over here, right? Methyl swings here, H here. Phenyl 2 at the bottom. OH here. And H here. When drawn with phenols at top and bottom, is it erythro or threo? High priority group here is O. High priority group here is carbon. What is it? Erythro. It's not meso because there's no plane of symmetry. What would the enantiomer be? Also erythro. It would just be the mirror image of this, which is also erythro. You only get erythro here. You do not get threo. This reaction is diastereoselective. But it's not enantioselective. All right. We'll see what any last questions on Monday.